control, cryptography, and high-speed computation. What are magnetic cores? They are tiny rings of nickel alloy or other magnetic materials. They have replaced vacuum tubes for many important functions in data processing systems. Cores come in a variety of sizes and in two basic types. The ferrite type of core is molded from compounds that magnetize easily and is used to provide data processing systems with their memories. The metallic ribbon type consists of a non-magnetic spool wound with a thin ribbon of highly magnetic alloy. This type is used in operating circuits of ADP systems. Both types of magnetic cores are remarkably adaptable to the language of data processing. Many ADP systems use the binary system of numbering, which employs just two digits, 0 and 1. These two digits are called binary digits, or bits for short. A bit is either a 0 or a 1, nothing else. Why do we use binary? Because a bit can be represented by any bistable device, and the magnetic core is a bistable device. Bistable, because it can be magnetized in two directions. When the magnetic lines of force point in one direction around the core, they are a positive magnetic flux, and the core is said to hold a binary 1. If the direction of magnetism is reversed, the flux becomes negative, and the core holds a binary 0. However, remember that this arbitrary definition of positive magnetic flux representing binary 1 and negative magnetic flux representing binary 0 may be reversed in some systems. So far, we've been establishing the function of magnetic cores. They store binary digits, or bits, 0 or 1. Now we're going to see how they do it, and also how they transfer bits from one core to another. To explain how cores store binary digits, we must know how they are constructed. Around the core is wrapped a conductor. Current flowing through the winding produces a magnetic field around the conductor. Because the core is made of highly permeable material, it forms a path for the magnetic lines of force. Because it is ring-shaped, the path it forms is a closed loop. The conductor here is wound so that current flowing in this direction produces a positive flux, setting the core in the binary 1 state. Current flowing in the opposite direction produces a negative flux, which sets the core in the binary 0 state. To show the polarity of the winding in a core diagram, we mark one side with a black dot. By definition, current that flows into the winding from the dot side sets the core to 0. Current flowing into the non-dot side sets the core to binary 1. Remember, non-dot current for 1 and dot current for 0. Any winding around the core obeys the laws of electromagnetism. The magnetizing force it exerts is proportional to the amount of current flowing through it, measured in amperes, times the number of turns in the coil. Or, as it is usually expressed, current. Suppose we increase the amount of current. Will the total magnetism of the core also increase? It will, but not proportionately, as we'll see on this graph. We're going to take a minute and trace the magnetization curve of a core, because in this way we can point out some of the characteristics that make cores so useful.